The idea that everything is made of tiny, indivisible particles is not new. It's believed to have originated with the Greek philosopher Leucippus and his student Democritus in the 5th century BC, and over the last 2,500 years, the idea has been refined by some of the greatest minds of each new generation. In this video, I would like to answer the following simple question. According to our most successful theory of physics, what exactly is a particle? Now, it turns out that the answer to this question is very easy to state. A particle is the smallest possible vibration of a quantum field. So if all you're after is a convenient soundbite, there you have it. If, however, you'd like to know what this sentence means, and along the way learn a little bit about one of the most successful scientific theories ever created, then stay tuned. In order to understand what a particle is, we're going to need a strategy. Firstly, we need to understand how to mathematically describe vibrations and waves. Next, we'll need to understand how quantum mechanics modifies our description of those vibrations and waves. Thirdly, we'll need to understand what a field is, and more specifically, a quantum field. And then finally, we'll be in a position to understand what a particle is according to quantum field theory. Our story begins with a series of experiments conducted by the scientist Robert Hooke, who, for reasons that are not particularly clear, decided one day to investigate the properties of helical springs. A spring is simply a piece of metal wire wrapped into a helical coil. Hooke wanted to investigate how the extension of a spring varied with the force applied. Consider an unstretched spring fixed at one end with a mass m attached to the other end. If you then pull on the mass and extend the spring by some amount x, the spring exerts a restoring force F on the mass, which tries to return the spring to its equilibrium length. Hooke discovered that the restoring force F is proportional to the extension x. In other words, if you double the extension, the restoring force doubles. We can write this as F is proportional to minus x. The minus sign simply tells us that the extension is in the opposite direction to the restoring force. We can then turn this proportionality relationship into an equality by introducing a constant of proportionality k. This constant is known as the spring constant and is a measure of how stiff the spring is. Next, consider what would happen if the spring was extended and then released. Clearly, the restoring force acting on the mass would cause the mass to accelerate according to Newton's second law, and therefore we can replace F with ma and write ma equals minus kx. If we then rearrange this expression, we get a equals minus k over mx. The statement that the acceleration is proportional to the negative of the displacement is what defines a special type of motion known as simple harmonic motion, a type of motion that lies at the heart of an incredible variety of vibrating systems in the physical universe. So let's delve a little deeper. In order to understand the dynamics of an oscillating spring, we will take the Hooke's law equation and rewrite it as a second-order differential equation, which will make it easier to analyse from a mathematical perspective. So how do we do this? Firstly, recall that acceleration is defined as the rate of change of velocity, which we can write as dv by dt. Furthermore, velocity is defined as the rate of change of displacement, and we can write that as dx by dt. And so if we combine these two definitions, we can write the acceleration as d by dt of dx by dt, which is conventionally written as d2x by dt squared. And the advantage of doing this is that we can now rewrite the Hooke's law equation as a second-order differential equation as d2x by dt squared equals minus k over mx. This differential equation describes how the displacement of our spring varies with time. So the natural question arises, what is the solution to this equation? In order to understand how the displacement varies with time, imagine displacing a mass attached to a spring and then releasing it and allowing it to oscillate freely. If we plot a graph with displacement on the y-axis and time on the x-axis, then we see a familiar pattern traced out in time. We recognise this function as a cosine function, and so we see that the displacement is proportional to cos of t. Let's consider this in a bit more detail. If we write the displacement function as x of t equals a cos omega t, then we see that a represents the amplitude or maximum displacement of the spring. This follows from the fact that cosine function can never be greater than 1, and therefore multiplying by a allows us to define the maximum displacement of our oscillating system. Next, the coefficient of t is referred to as the angular frequency, measured in radians. We can formally define the angular frequency omega as 2 pi divided by t, where t is the time taken for one complete oscillation, or cycle, of the spring. Finally, we can write this in terms of the normal frequency f, where f is simply the number of complete oscillations or cycles per second. And so we see that an alternative way of writing the displacement function is as x of t equals a cos 2 pi ft. Now that we have an expression for the displacement function, we should check that it does indeed represent a solution to our second order differential equation. So how do we check? Well, we simply need to substitute x of t equals a cos omega t into our differential equation and see if the left and right hand sides match. So let's do this. The first thing that we notice is that the left hand side requires us to differentiate our displacement function twice with respect to time. And since the displacement function involves a cosine function, it would be helpful to recall the rules for differentiating cos and sine functions. If we differentiate the displacement function once with respect to time, then we find dx by dt equals minus a omega sine omega t, and this function represents the velocity of our simple harmonic oscillator. Next, if we differentiate again with respect to t, then we find that d2x by dt squared equals minus omega squared a cos omega t, which is simply equal to minus omega squared x. And so we see that by substituting the displacement function into our differential equation, we find that minus omega squared equals minus k over mx. If we cancel the x's from both sides and rearrange for omega, we find that omega equals the square root of k over m. In other words, our proposed displacement function is indeed a solution to the SHM differential equation, provided the angular frequency is related to the spring constant and mass in this particular way. So what is this constraint telling us? We can shed some light on the interpretation of this constraint by rewriting it in terms of the time period and frequency of our spring. Rearranging for f, we find that the frequency of our oscillating spring is equal to 1 over 2 pi times the square root of k over m, and rearranging for t, we find that the time period of our oscillating spring is equal to 2 pi times the square root of m over k. It's worth emphasizing just how remarkable these statements are. These equations allow us to theoretically predict the frequency and time period of an oscillating mass, provided we know the mass and spring constant, both of which are easy to measure. Our next step is to understand how much energy is contained within an oscillating system. The total energy of our oscillating spring will be equal to the sum of the kinetic energy and the potential energy of our system. The kinetic energy is due to the motion of the spring, and the potential energy is due to the spring being stretched or compressed. As you probably recall from school, the kinetic energy is simply equal to half mv squared, whereas the potential energy is equal to half kx squared. By rewriting the velocity in terms of x, we see that the energy is equal to half m dx by dt all squared plus half kx squared. If we then substitute the displacement function, we arrive at this rather beautiful yellow expression. Next, we can use the constraint equation linking omega, k and m to rewrite k as m omega squared. The reason for doing this is that it allows us to pull out a factor of half m omega squared a squared, and then we see that the term inside the bracket is sine squared omega t plus cos squared omega t, which is simply equal to 1. And so once the dust is settled, we find that the total energy of our harmonic oscillator is equal to 2 pi squared f squared a squared m. Notice that although both the kinetic and potential energy were functions of time, the total energy is not a function of time. In other words, the total energy remains constant in time. This is simply a statement of the conservation of energy. We also see that the energy of a classical oscillating spring is proportional to the frequency squared multiplied by the amplitude squared. And so we see that the energy of a classical oscillating spring can take any value, since the amplitude can vary continuously. What we now want to do is see if this is still true once we incorporate quantum mechanics. So let's do that. One of the greatest revolutions in physics occurred at the beginning of the 20th century when Max Planck suggested that rather than energy being a continuous quantity, as had been assumed for centuries, it was in fact discrete. Planck suggested that if an oscillating system had frequency f, then the energy of the oscillator could only ever be an integer multiple of Planck's constant, multiplied by the frequency of oscillation. According to this new quantum framework, n refers to the number of quanta of oscillation in the system. By adding additional quanta, the overall energy of the oscillating system increases in discrete chunks, with each chunk being equal to hf. Planck originally proposed this revolutionary idea to solve the famous ultraviolet catastrophe, but the idea was soon picked up by Einstein and applied to the photoelectric effect, and the idea of energy quantization now lies at the heart of quantum mechanics and quantum field theory, as we will see. So how does this affect our oscillating spring? Well, the remarkable thing is that if you apply quantum mechanics to a simple harmonic oscillator, then the oscillating system can no longer have any amplitude, but only certain discrete values of amplitude. To see this, let's combine the expression we derive for the classical energy of an oscillating spring with Planck's quantum energy expression. Combining these two equations, we find the following green expression. If we then rearrange for A, we see that the amplitude of a quantum oscillator is equal to 1 over 2 pi multiplied by the square root of 2nh over mf. And so we see that depending on the integer value of n, both the energy and amplitude of the oscillator can only take certain values. So why don't we notice this in everyday life? To see why, let's put a few numbers into our amplitude equation. If we have a 100-gram mass oscillating with a frequency of 1 Hz or once per second, then we find that the difference between each allowed amplitude is 1.8 times 10 to the minus 17 meters, which is smaller than the diameter of a nucleus. In other words, from our perspective, for all intents and purposes the amplitude varies continuously, and so we just don't notice. This is in large part due to the fact that we are considering a macroscopic system. We will shortly see that quantization plays a fundamental role when we consider nature on the smallest of scales. Now, it is worth mentioning that the quantum mechanical analysis that we've completed so far is a bit simplistic and doesn't actually capture the full story of the quantum oscillator. To probe a little deeper, let's reconsider our expression for the energy of an oscillator and rewrite the kinetic energy in terms of the momentum. Only this time, let's think about one of the other great discoveries of the early 20th century, Heisenberg's uncertainty principle. According to Heisenberg's uncertainty principle, there is a limit to how accurately we can simultaneously know the position and momentum of a system, and this inherent uncertainty is encoded in the famous relation delta x times delta p is greater than or equal to h bar divided by 2, where h bar is the reduced Planck's constant. In the case of our oscillating mass spring system, if delta x represents the uncertainty in the location of the spring, then delta p represents the uncertainty in the momentum of the spring. Now, according to classical physics, if the spring is unextended and at rest, then there is no uncertainty in where the spring is or the spring's momentum, and so the total energy of the spring is zero, as can be seen from setting both p and x equal to zero in the classical energy expression. However, according to Heisenberg's uncertainty principle, it's not possible for either delta x or delta p to be zero, and so there is always an inherent quantum jittery motion in the spring, even when unextended and classically at rest. To see this in detail, let us calculate the energy uncertainty in our oscillator by replacing x with delta x and p with delta p in the classical energy expression. If we then minimize the energy uncertainty with respect to position uncertainty by differentiating this expression and setting it equal to zero, then we see that the position uncertainty can be expressed as the square root of h bar divided by 2m omega. If we then substitute this back into the energy uncertainty relation and simplify, then we see that the energy uncertainty is greater than or equal to half times hf. and therefore the minimum energy of a quantum oscillator is equal to half hf. This minimum quantum energy is known as zero-point energy and is an important consequence of quantum mechanics. In the context of our analysis, we therefore need to modify the quantum energy expression for a quantum oscillator. Instead of E equals nhf, we should factor in the zero-point energy and write E equals n plus half times hf. Note that the amount of energy required to add one quantum of oscillation is still hf as before. We won't often need to pay attention to this little shift in n, however, it is worth noting that this shift is very interesting and lies at the heart of one of the great unsolved mysteries of physics, known as the cosmological constant problem. But that discussion will have to wait for another day. Now that we have a basic understanding of simple harmonic motion, both classical and quantum, we can turn our attention to the related phenomenon of wave motion. A wave can be thought of as a propagating disturbance that transports energy and information from one place to another without transferring matter. Classical waves can be categorized as either mechanical or electromagnetic. Mechanical waves require a medium through which to travel, whereas electromagnetic waves do not. Now we can describe the displacement of a wave in the y direction as a function of position x and time t using the following expression. Omega is the angular frequency, which we've already seen, and k is referred to as the wave number, which defines the spatial frequency of the wave. If we focus in on a particular fixed x value, then the wave displacement equation reduces to the displacement function of a simple harmonic oscillator. It is in this sense that you can think of a wave as simply a series of coupled harmonic oscillators. Now, in much the same way that the displacement function for a harmonic oscillator was a solution to a differential equation, the displacement function for a propagating wave is also the solution to a very famous differential equation, appropriately named the wave equation. The wave equation is second order in both space and time derivatives, and also contains information about the velocity of the wave. We can test that the displacement function is indeed a solution to the wave equation by substitution. Differentiating the displacement function twice with respect to time gives a factor of omega squared, whereas differentiating twice with respect to x gives a factor of k squared. If we then simplify, we find that omega squared equals v squared k squared. If we then rearrange for v and sub in the definitions for omega and k, then we see that v equals f lambda, which is the familiar wave relationship that every child learns about in school. Here, we see that this relation arises as a constraint produced by the wave equation. It will prove convenient for comparison later to emphasize a few important features of this wave equation. Firstly, notice that we can rewrite the wave equation with all terms on the left-hand side. The rationale for doing this will be revealed in a moment. It's also worth mentioning that for a given system, the wave equation predicts that all waves travel at the same speed v. It then follows from the constraint equation v equals f lambda that the frequency and wavelength can take any value. And finally, the amplitude of these waves can, in principle, also take any value. Unsurprisingly, this situation changes once quantum mechanics is factored in, and we will look at quantum waves shortly. Before doing so, it's worth pausing a moment and considering whether it's possible to modify our wave equation, and if so, what effect this might have on the relationship between speed, wavelength, and frequency. A natural extension to the wave equation is to consider the addition of a linear term in y, as can be seen in the boxed equation. The rationale behind this specific form of coefficient will become clear shortly. What we now wish to do is understand the effect of this modification on the constraint equation which links velocity, frequency, and wavelength. In order to reveal what's going on, let's substitute the wave displacement function into this new modified equation and see what we get. A simple calculation reveals that, upon substitution, we find minus omega squared plus v squared k squared equals minus 2 pi chi all squared. If we then sub in the definitions of omega and k, we can then rewrite this expression in terms of the frequency and wavelength. If we then simplify this expression and then rearrange for f, we find the following expression for the frequency of the modified wave. Firstly, we notice that if we set chi equal to 0, then we simply recover the familiar relationship between frequency, wavelength and speed corresponding to the unmodified wave equation. If, however, chi is non-zero, then we see something very interesting emerges. Because v over lambda, which appears in the first term inside the square root, must always be positive, it follows that the frequency f must always be greater than or equal to chi. In other words, chi represents the minimum possible frequency of this type of wave. So what we have discovered is that by modifying the wave equation and adding a linear term, a constraint is placed on the lowest possible frequency of the waves permitted by the equation. And so from now on, we will write our modified wave equation explicitly in terms of the minimum frequency. This minimum frequency condition is going to play a fundamentally important role in our analysis and interpretation of quantum fields, and in our understanding of what a fundamental particle is. But before we get ahead of ourselves, let's first investigate how to calculate the energy of a wave, both classically and quantum mechanically. In order to calculate the energy of a wave, we will consider the specific example of a rope with mass per unit length mu. Next, imagine sending a series of transverse waves along the rope and then focus on a small section of rope of length dx. Because the waves are transverse, the displacement of the rope will always be at right angles to the direction of wave propagation, and therefore this small section of rope will move upwards and downwards in the y direction. If the velocity in the y direction is labelled v subscript y, then we can write down an expression for the kinetic energy of this segment, where dm is the mass of the small segment, which can be written as mu times dx, and vy can be written as dy by dt, where y is the wave displacement. If we then substitute the wave displacement function, we can rewrite the velocity as a omega sine kx minus omega t, and so if we put everything together, we finally arrive at the following red expression. Next, we wish to write an expression for the potential energy of the wave. If we focus in on a small segment of rope, then we can calculate the potential energy by calculating the work done as the rope stretches, which is simply equal to the force times the extension. We can see from the diagram that if dx represents the unstretched length of the segment of rope, then the extension of the rope can be approximated as the difference between ds and dx. Then if T is the tension acting on the small segment, it follows that the potential energy will be equal to T times ds minus dx. We can write this rather more suggestively as T times the square root of dx squared plus dy squared minus dx. And then if we take out a factor of dx from inside the square root, we finally arrive at the following blue expression. Because we are dealing with a small segment of rope, we can perform a binomial expansion on the square root and approximate it as 1 plus half times dy by dx all squared. If we do this, we see that the 1's cancel, and we can write the potential energy of our segment as half times t times dy by dx all squared dx. Next, we can sub in the well-known wave displacement function, and we arrive at this light green expression. Finally, by combining this with our expression for the kinetic energy, we can write the total energy of our rope segment as dE equals mu times omega squared a squared sine squared kx minus omega t dx. It is now a straightforward task to calculate the energy contained within one wavelength of our wave. To do that, we simply need to integrate our expression for dE from 0 to lambda, where lambda is the wavelength. The trick to integrating this expression is to recall that sine squared x equals half times 1 minus cos 2x, and a simple calculation then leads to the following expression for the energy per wavelength. If we write this in terms of the frequency f, we find that the energy per wavelength is 2 pi squared f squared a squared mu. And the remarkable thing that we notice is that the energy of a wave is proportional to the frequency squared multiplied by the amplitude squared, which was exactly what we found for our simple harmonic oscillator. This shouldn't come as too much of a surprise, since a wave is nothing other than a series of coupled harmonic oscillators. Now, it is worth mentioning that although we based our analysis on the specific example of a rope, this analysis generalizes to waves travelling through all sorts of media, and in all cases the same relationship between energy, frequency and amplitude holds true, as it should for all simple harmonic motion. So the natural question arises, If the energy of waves and harmonic oscillators obey the same relationship, is the same true when we factor in quantum mechanics? How do we describe a quantum wave? Well, it turns out that it's relatively straightforward. Since a wave is simply a series of coupled harmonic oscillators, it follows that the properties of a quantum wave are very similar to the properties of the quantum oscillator. In particular, the energy of a quantum wave can be expressed in terms of Planck's constant and the frequency as n plus half times hf, where n tells us how many quanta of oscillation we have in our wave. And we see that each quantum of a wave carries energy equal to hf. Next, we can equate this quantized energy with the expression we just derived for a wave. Imagine that we have a wave of wavelength lambda that extends over a region of length L. Then clearly there will be L over lambda crests or wavelengths within this region, and therefore we can write the total energy in this region as follows. And this is essentially equal to nhf, as for large values of n we can safely ignore the contribution of the 0-point energy. If we then rearrange this expression for the amplitude A, we find the following blue expression, and we see that the quantum mechanics restricts the amplitude of the wave to discrete values, just like for the oscillation of a spring. So what does this imply for our two types of wave equation that we encountered earlier? If you recall, the unmodified wave equation gave rise to the constraint f equals v over lambda, and this constraint implies that the frequency of this type of wave can take any value. This in turn implies that a quantum of this type of wave can in principle also have any energy. This means that even if there is a small amount of energy available, it is still possible to make a quantum of this type of wave provided the frequency is low enough. However, we have also seen that by modifying the wave equation and adding a linear term, we arrive at a different constraint equation, which implies that waves obeying this equation have a minimum possible frequency. Now the key point is that when we add quantum mechanics into the mix, this minimum frequency constraint translates into a constraint on the minimum energy that a quantum of this type of wave can have. In particular, we see that the minimum energy of a single quantum is Planck's constant times the minimum frequency. And it follows that if the available energy in our system is less than the minimum quantum energy, then you cannot make a single quantum of this type of wave. And this simple fact is going to play a crucial role in our analysis of quantum fields. So what exactly is a field? In physics, a field is simply a function of space and time with an associated equation of motion that describes how the function may change with time. Now the simplest kind of field is a scalar field, which simply consists of a number assigned to each point in space. For example, if you were to measure the temperature at every point in space, then we could define a temperature field by assigning a number to every point. To help visualize this, we might use a color gradient, and we could then use an equation such as the heat equation to understand how the numbers change in the presence of a new or changing heat source. Another important type of field is known as a vector field, in which we assign both a number and direction to each point in space. For example, if you were to measure the wind speed and direction at every point in space, then you could produce a map consisting of arrows located at each point in space, with the length of the arrow being proportional to the speed, and the direction of the arrow indicating the direction of the wind at that point. Another classic example of a vector field is the electric field, which exists around electric charges. In this case, the arrows at each point show the direction and magnitude of force that would act on a positive test charge if placed at that point. Furthermore, we see that if an electric charge moves, then the field changes and updates in accordance with the new charge location. Now it turns out that if a charged particle accelerates, for example, if it moves in a circle, then this causes the field to ripple, sending a disturbance through space. In the case of the electric field, these ripples are in fact light waves which travel at the speed of light. It was during the 19th century that James Clerk Maxwell first discovered that it was possible to combine the equations of electricity and magnetism to arrive at a wave equation which predicted the speed of electromagnetic waves should be 300 million meters per second. The remarkable thing was that this speed perfectly matched the recently measured speed of light, leading Maxwell to conclude that light is an electromagnetic wave. Now a natural question to ask is if light is travelling at 3 × 10⁸ meters per second, then relative to which frame of reference is this velocity measured? This was, in essence, the question considered by Einstein whilst working on his theory of special relativity at the beginning of the 20th century. One of the key features of Einstein's radical theory was that all observers would measure the same velocity of light, irrespective of their frame of reference, implying that different observers would measure the passage of time differently according to their relative motion. Furthermore, according to Einstein's theory, it was possible for light to travel at a constant speed through empty space without a medium to support it. According to this picture of reality, an electromagnetic wave is a self-propagating ripple of an underlying relativistic field, namely the electromagnetic field. Now, it turns out that the electromagnetic field is not the only example of a relativistic field. There are in fact two broad classes of relativistic fields which we are going to focus on, corresponding to the unmodified and modified wave equations that we encountered earlier. The only difference now is that we're going to label our relativistic field function using psi, and c refers to the speed of light. So what exactly are these equations describing? Well, firstly, both of these relativistic wave equations describe waves that carry information and energy from one point in space to another. Furthermore, it's important to emphasize that a relativistic field does not describe the property of some ordinary physical medium. There is no underlying medium. In fact, as far as we can tell, relativistic fields may be among the most fundamental elements of reality. And so we are almost in a position to finally understand what a fundamental particle is. All we need to do is combine our knowledge of relativistic fields with our knowledge of quantum mechanics. So let's do this. We will begin by focusing on the modified relativistic field equation. We have already seen that the frequency of the waves in such a field are constrained and there is a lowest possible frequency. If we square both sides of this constraint equation, then we find a Pythagorean relationship, which is always a good sign in physics. What we now want to do is take our Pythagorean constraint and combine it with the energy relation for a single quantum. If we multiply both sides of our frequency constraint equation by Planck's constant and make use of E equals hf, then we arrive at the following total energy relationship. Now, hopefully, if you've watched my video on Einstein's theory of special relativity, then the form of this equation should remind you of the famous energy-momentum relationship from Einstein's theory. According to Einstein, the energy E of an object or particle is related to its momentum p by the equation E squared equals p squared c squared plus m squared c to the 4, where mc squared is the rest mass energy of the particle, which exists even if the object is not moving, and therefore you can think of the rest mass energy as the minimum energy that the object can have. Now, we've also seen that waves obeying the modified relativistic field equation have a minimum frequency, and furthermore, according to quantum mechanics, this implies that a quantum of this field has a minimum energy of Planck's constant times the minimum frequency. And so it's very tempting to equate mc squared with Planck's constant times the minimum frequency. And it's also tempting to equate the first two terms in each of these expressions and set p squared c squared equal to hc over lambda all squared. So what are these relationships telling us? Well, if we begin by rearranging the second equation, then we recover the famous de Broglie relationship linking the particle property of momentum with the wave property of wavelength. But what about the first relationship? Well, if we rearrange for m, then we see something truly remarkable. This equation is telling us the mass of a quantum of this type of relativistic field. In other words, we see that any particle with mass can be thought of as a quantum of a relativistic field whose waves have a minimum frequency and therefore a minimum energy. And furthermore, we see that what we refer to as mass is simply the minimum energy of a vibration of the quantum field divided by the speed of light squared, which is a truly remarkable revelation. But what about massless particles? How can we describe those? Well, we see from the mass equation that if the minimum frequency is set to 0, then the mass also becomes 0. And this fits with what we have already seen, because if you recall, there is no minimum frequency constraint in the unmodified wave equation, and furthermore, we know that light, which is massless, is described by the unmodified wave equation. So if we set the minimum frequency to 0, then we see that not only is the mass zero, but we also recover the familiar photon-energy relationship that Einstein introduced to explain the photoelectric effect. And finally, if we set the mass equal to zero in the energy-momentum relationship, we recover the familiar expression for the momentum of a massless photon. And so now we are finally in a position to answer the question that was posed at the beginning of the video. What is a particle? Hopefully, if you followed this far, then you'll be in a position to understand that a fundamental particle is simply the smallest possible vibration, or quantum, of a relativistic quantum field. And furthermore, we have seen that particles with mass are described by the modified relativistic wave equation, whereas massless particles are described by the unmodified relativistic wave equation. And it is this view of reality that lies at the heart of the standard model of particle physics. Within this framework, the quantum fields are considered fundamental, and the familiar particles of the standard model appear as the quanta of these fields. For example, the smallest possible vibration in the electron field is called an electron. Similarly, the smallest possible vibration in the electromagnetic field is a photon. And then there are quark fields and gluon fields and a Higgs field. And so we see that every particle in the universe is a tiny quantum mechanical ripple of the underlying relativistic field. And that is where our journey ends, for now. Of course, there are still many questions left to answer. For example, what determines the minimum frequency of our modified wave equation? Why do some particles have mass, whereas others are massless? How do quantum fields interact with one another, and what is the relationship between matter and antimatter? Answers to all these questions exist within the highly successful framework of quantum field theory, and will no doubt form the basis of future videos on this topic. For now, however, I think it only appropriate to end with a quote by one of the pioneers of quantum theory, Wolfgang Pauli. The best that most of us can hope to achieve in physics is simply to misunderstand at a deeper level. Well, I hope that I've helped to deepen your misunderstanding with this video. Thanks for watching.